Hello, I'm going to look at topic D here, which is fluid systems essentially. So we've got questions about dams, questions about pipes or tapering pipes, and then questions about buoyancy, Archimedes principle. Okay, so we'll look at the exam questions and see how we approach them. This is the section of the datasheet that you'll be using. So volumetric flow and mass flow are related to your pipes or your tapering pipes. Hydrostatic thrust is related to dams, and density can crop up anywhere. You'll notice there's not a formula for Archimedes principle there, but we'll get to that in a second. Alright, here's the first one. State one factor affecting the flow rate of a liquid in a section of gradually tapering pipe. So here's the section of the datasheet for fluids. So the tapering pipe, as I mentioned, was these first two. So essentially gets to go for the easier one, and it's the cross-sectional area, that's A, or V. Now V is velocity there. So either one of those, there you go, area, velocity. Don't worry about the rest, just go for the factors that are in the formula, the relevant formula. Okay, so here is one on Archimedes principle. You've got something that's being put into a liquid, so it's either going to be floating or sinking or something like that. So we call them immersed bodies, and you have something here. Now the key thing about this question is that it's in static equilibrium. So it's fully submerged in static equilibrium. Now if you went back here to this part of the data sheet here, you wouldn't find anything on Archimedes principle. As I said, this is the thing that you need to remember: upwalled. So anytime you see something about submerged bodies or immersed bodies, you would write upwalled. So the up thrust is equal to the weight of the liquid displaced. And you've also got to spot that the up thrust is also the apparent loss of weight. So, a little bit of theory here, because we've got something that's fully submerged and it's in static equilibrium. That means it's floating, but it's fully in the water. So it's essentially weightless. So it's lost all of its weight. Which means if you can figure out the apparent loss in weight, then that will allow you to get the weight of the actual object, because they'll be equal. It's lost all of its weight. So, upwalled, the up thrust, or the apparent loss of weight, is equal to the weight of the liquid displaced. Well, they've given you the weight of the liquid displaced. It's 22 newtons. So that tells you that the weight of the object is 22 newtons. So, yeah, more straightforward than it looks. Why is it worth 9 marks, I suppose? Because you're not asked for its weight, you're asked for the density. So, that is given to you. Density is mass over volume. So you've got to work out its volume, the volume of a cylinder, which is in the data sheet, and you've also got to work out its mass. Well, that comes from weight equals mass times gravity, so it'll be weight divided by gravity, but the weight is 22 newtons. So there's a bit to do there, but I suppose the theory is understanding that, understanding this. The weight of the liquid displaced is equal to the apparent loss of weight, and if it's floating and it's completely submerged, then that's all of its weight. Okay. And there's the other two. Density equals mass over volume is given to you. I tend to use these a lot, but weight equals mass times gravity is something that you'd use in these questions as well, because it asks you to get density, which involves mass, and you've got weight. Weight is in newtons, it's a force. Mass is measured in kilograms. Here's the mark scheme. Okay, identify the name of the unit of hydrostatic pressure. Well, we did do this theory when you study hydrostatic thrust, and pressure is force over area, and force over area is otherwise known as a Pascal. Right, here's your fluids. So we have a tapering pipe. It doesn't show you the tapering pipe, it shows you the cross-sectional area at one section of the pipe, and then it gets thinner, and there's the cross-sectional area at the second section of the pipe. and it asks you to calculate the outlet flow velocity. So it's a tapering pipe, so hopefully you'd find fluid principles here, and then we've got this continuity of volumetric flow or continuity of mass flow. Now it's not a classic formula. It's not like A equals B times C or B divided by C. You've got two things on the left and two things on the right, which is kind of equating really. It's saying that one value is equal to the other value. So this is the volumetric flow at the start, and this is the volumetric flow at the end. So it's saying they're equal. So the area times the velocity at the start, area, 0.5 times velocity, 15, is equal to the area times the velocity at the end. Okay? Area times the velocity at the end. The area, 0.3. Velocity, well, that's what you've been asked for. So 0.5 times 15 is equal to 0.3 times the value you've been asked for. So if you divide both sides by A2, that will give you your final velocity. Okay, so yeah, I suppose you might argue that it's a little bit trickier because it hasn't just got a single subject of the equation, but essentially all you've got to do is remember that A is your cross-sectional area and V is your velocity. Obviously they've been quite kind to you here. They've given you the area rather than the diameter or the radius, and I think it's probably more common to give you the diameter there, so you have to work out the area. Okay, here's a dam. So as I said, dam, you want to be looking for this third one down here. Hydrostatic thrust on an immersed plane surface. So yeah, it'd be nice if that just said dams, thrust on a dam or force on a dam. Thrust is a force. So that's the thrust. It's rho GAX. Okay? So you would just write force equals rho AGX. Here though, they start you off on point 1, calculate the area of the water against the dam. So it's the height times the width, 8 times 6. And then they want the hydrostatic thrust. So it is just rho GAX. Rho is density, but that tells you underneath, density, rho. G is given to you here in physical constants. So this is in your datasheet. The G is 9.81. A is your area. Well, you worked that out in part 1, didn't you? That's the answer to part 1. That's the height times the width. But that's the height times the width of the water that's in contact with the dam. Doesn't matter how tall the dam is, what matters is how high the water goes. And then finally you've got X. Now, X for a dam, for water on the dam, when you're calculating the thrust, X is halfway up. So just remember that for the exam. It's halfway up. So X would be 3 meters in this case. Okay, so in this case it would be rho GAX 1000 times 9.81 times 6 times 48 times 3. And that will give you the hydrostatic thrust. Thrust is a force, so the units are newtons. And there's the mark scheme. Next we have really just a simple density question, but the volume of the spherical component, this is just from topic A, working out the volume of a sphere, which is given to you on page 3. So it's 4/3 pi r cubed, and once you've got the volume of that sphere, the density is just mass over volume. So you're given the mass, there we go, so divide it by your answer to part 1. The mark scheme. Here's another tapering pipe. So the pipe will change its diameter. So they want the cross-sectional area of the outlet. So as I pointed out before, it's more likely that they give you a diameter or a radius, and then you can get the cross-sectional area. So the diameter is 60 millimeters. I would straight away change the milli to times 10 to the minus 3. So it's 60 times 10 to the minus 3. Divided by 2 to get the radius, 30 times 10 to the minus 3, and then pi r squared gives you the cross-sectional area. Part 2 asks you for the mass flow rate of the fluid. So that's rho AV. Now this is not a formula for mass flow rate, it's continuity of mass flow rate. What this says is mass flow rate at one point equals the mass flow rate at your second point. But this question isn't as complex as that. It just asks for the mass flow rate, which is one side of the formula, rho AV. Rho is the density of the fluid, which is 1000. A is the cross-sectional area, which you've calculated in part 1, and V is the velocity, which is 2. So that one's pretty straightforward. Okay, so here's another dam. Now this is this was on the 2017 paper, the first proper paper that came out, and more challenging than the dams in recent times. So you're asked for the moment, but you'd start just thinking, right, it's dams. So here we go. I'll go to hydrostatic thrust on an immersed plane surface, rho g AX. So you'd have to work it out on the left and on the right as well. So F equals rho g AX on the left hand side. Rho, it's fresh water, so rho's 1000. G, 9.81. A, 4 times 10. X, halfway up, 2. You'd do the same on the right hand side for seawater. So rho, density, 1030. G, 9.81. A is 1.5 times 10. And X, halfway up, 0.75 meters. So that would give you the hydrostatic thrust on the left and the hydrostatic thrust on the right. But they ask you for the resultant turning moment. So you need to remember this formula if this did crop up. Moment is force times distance. It's the distance from the pivot, and for a retaining wall, you'd take the pivot as this. If it was going to topple, it would pivot around here, wouldn't it? So there's your pivot. So just got to try and remember this really. X is always halfway up, but your distance from pivot will be 1/3 of the way up. Now we've done the theory and lessons about that, but at this late stage for the exam, just remember, if you calculate in a moment, it's just 1/3 of the way up. So your force you've calculated, so just times that by distance from pivot. So whatever you've worked out as the force on the left hand side, times it by 1/3 of the way up, so 4/3. And then whatever you have on the right hand side, whatever your force was on the right hand side, times it by 1/3 of the way up, 0.5. This side will give you a clockwise moment, that side will give you an anti-clockwise moment. They ask for resultant. So subtract the anti-clockwise away from the clockwise. And yeah, it does seem a fair bit for 6 marks there, I suppose. But as long as you can get the hydrostatic thrust, then you're covering your bases for most of the questions. There's your mark scheme. Okay, another dam question. Just simply asking for the hydrostatic thrust on the dam. Again, straight to fluids. Third one down, hydrostatic thrust on immersed plane surface, rho g AX. Rho is your density, 1000. G, 9.81. A, 10 times 5. X, halfway up, 5. Okay, it's hydrostatic thrust, which is a force. Your units are newtons. Right, here's a pipe. It's getting thinner, isn't it? So we have a diameter of 50 millimeters, which tapers or thins to a diameter of 40 millimeters. You've got the initial velocity, and you're asked for the final velocity. Okay, so here's your formula here. Area times velocity at the start equals area times velocity at the end. But of course you don't have the area. So first thing you should do would work out the area at the start. So 50 millimeters is the diameter. So change the milli to times 10 to the minus 3 and then halve it. So your radius is 25 meters. 25 millimeters, or 25 times 10 to the minus 3 meters. And then pi r squared gives you your area. So if you've calculated the area on the left hand side, the area on the right hand side, so then it would just be the area on the left hand side times the velocity on the left hand side equals the area on the right hand side times the velocity on the right hand side. So that would allow you to work out the velocity here. You would divide both sides by A2. Okay, now Archimedes' principle is this thing about upwall. Essentially, all you are saying is that upwall thing that I put on before. So your upthrust, which is the apparent loss of weight of a body placed in a fluid, is equal to the weight of the liquid displaced. That's all it is. And then here, the weight of the solid metal component is known to be 2,200 newtons in air and 2,000 newtons when immersed in water. Calculate the relative density of the component. Well, relative density is not on your data sheet, and even in the textbook it would state relative density equals the density of the substance divided by the density of the water. But the questions that have cropped up in the exam, you would approach it in a slightly different way, where the relative density of the substance is the weight of the object divided by the loss of weight in water. So, the relative density here, if the object is 2,200 newtons, and then it's 2,000 newtons when immersed in water, then the common error would be to do 2,200 divided by 2,000. We don't do that. It would be the weight of the object divided by its loss in weight. So the relative density there will be 2,200 divided by 200. That's how much it appears to have lost in weight. Relative density is a weight divided by a weight, or a density divided by a density, so the units cancel out. There would be no units, it's just a ratio. Okay, so that would be 2,200 divided by 200. Okay, that's your lot for topic D, which would be referred to as fluid systems, really. Dams, Archimedes' principle, and pipes. Thank you.